Now, you could use any logarithm you want, to be honest, but the natural logarithm is definitely the, well, it's just the easiest. Common logarithm would also work, but, and so that's the strategy I need to use here with this problem. So this is kind of like a checklist maybe, or like a flow chart, right? Start with this. If that doesn't work, go to this. If that doesn't work, then we have to go to this. So our strategy there is I take the natural log of both sides. The properties of logarithms then allow me to pull those exponents out in front as factors, right, or multiplication. And that's good because now this is just a bunch of values multiplied together. So 2x ln of 3 equals x times the ln of 7 plus the ln of 7. I can, move this over. Then I can pull the x out and divide by what's left. This would be the exact answer. I think for this problem, they want you to approximate the answer to 3 decimal places. So you do this on a calculator and get an approximate value there. Okay. Other questions on this example?
Where did the x go? Oh, never mind. I see it. Okay, so like,
Is that,
yeah, so the x just shifts over and yeah, okay.
yeah, I
That
kind of,
makes sense.
yeah, I did skip a tiny step there, right? I could have, probably should have written it like that first, right? And then divided to get that last step. So anytime you've got a problem like this where you got a bunch of different terms out there, just collect all the terms that have the variable you care about on one side, right? And then factor that variable out and divide. So that's how you can solve for that. It appears to be messy, but it's really not. The natural log of 7 is a number. It's a decimal, so it's a little harder to write down, but you really just want to think of it as like it's 12 or something, right? And what would you do if you had a 12 here and a 4 here or whatever, right? Well, you do these same steps here to get to this answer. Any other questions or steps that were unclear? Okay. There was also a question about continuously compounded interest. Remember, when you have continuously compounded interest, that gives me the formula P e to the RT. If it's compounded monthly or weekly or any other kind of compounding period, then it's that other formula, right? I'll just make a note of it over here. A equals P 1 plus R over N to the NT. So that's where you have compounding periods like 12 in a year or 1 in a year, whatever it might be. But this one is continuously compounded. And so what they often do is they give you like a couple different pieces of values here and ask you to kind of find other parts. So in this problem, they're going to give you some initial investment, which is P. Let's say that's $600. And then they give you some accumulated amount, which is, let's say, $1,205 after 10 years. So they're sort of giving you pieces of this, and you've got to find what's missing. So I'm going to start by just plugging in the parts that I'm told here. 1205 is the accumulated amount. 600 is the principal. I don't know the rate, but they said that was after 10 years. So this is also an exponential equation that I have to solve. If I go back to the strategy here, I can see, well, the two sides aren't both exponential equations, so I can't use that one. But it looks like it's going to fit number 2. I got to divide by 600 here to make it fit that pattern. And let me see what that is. It's close to 2, right? But we do want to be precise with these. You've probably experienced, I've had quite a few questions. You've probably experienced that if you make a tiny little rounding error, you're going to get the wrong answer. So I get 2.0083. So I'm going to keep quite a few decimal places when I do this work, and then finish rounding at the very end. So this one is perfect, right, to convert. I have an exponential equal to a number, so I can change that to the log base e, which is the natural log of 2.0083 equals 10r. And that's converting from the exponential to the logarithmic. So whatever that is divided by 10. See here. Log 2.0083, natural log of that divided by 10 equals, I forgot to write that down, right? But 0.06972. This is rounded to 2 decimal places, so that would be 0.07. Although as a rate, well, let me make that, this is, sorry, that's bad rounding. The rate is going to be as a percent. So as a percent, this is 6.972%. So rounded to 2 decimal places would be 6.97%. Be a little careful with that if it's depending how it's asked. Luckily for you, I'm not too picky about the rounding. The second part in this problem, particular problem, asks us the time to double. So it's really the same kind of problem, and it's going to be very similar, right? This took 10 years to almost double. Right, so I know my answer is going to be really close to 10 years, maybe just a tiny bit under 10 years. But the way I figure out doubling is I can just let the initial amount be anything I want, say 100. I have my rate 0.06 0.97t. I don't know what t is, right? I don't know what the time is. And that should double, so that should be equal to $200. It turns out it doesn't matter with exponential growth. It doesn't matter what values are here. I mean, the relationship matters, but as long as this one is double what you started with, you're going to get the same time no matter what you do. Because you can see it here, right? When I divide both sides by 100, this is going to be 2. Right? It doesn't matter if I started with 100, 200, or 1 million, 2 million, or whatever it is. As long as this is double what this is, I'm always going to get to this equation right here. Just like the previous one, I can solve this one by rewriting it as a natural log. Divide. You can check it on the calculator, but that's going to be very close to 10. Any questions on this example?
Can you go over the double part again, please?
Like, yeah. So I'm using the same exponential or this continuously compounded interest part here. And I found the rate. And then this particular question says, how long does it take to double? And so I just go back to my same formula, but I put in a principal and an amount where the amount is double the principal. So I just always pick 100 and 200 just because I find that easiest, but you could do 1 and 2 or 2,000 and 1,000, whatever it is. I want to know what value of t makes this equation true. Right? Does 100 times that equal 200? Double.
Got it. Thank you.
Okay, and then from there it's solving that equation. And actually, you know, that's one of the ways of describing exponential growth. It's actually if you have a quantity that doubles at a fixed amount of time, that's growing exponentially. And you may have seen some of those, you know, with the pandemic, some of the bad news parts of the pandemic, you'll see them say that it's, you know, the growth is accelerating. You know, it takes this long to get to 50,000 and this much shorter time to get the next 50,000. That's really, again, because it's doubling, right, in effect, in this sort of effectively fixed amount of time. So if you know how long it takes to go from 200 to 400, it takes the same amount of time to go from 400 to 800, 800 to 1600, 1600 to 3200, right? All of those intervals happen at the same amount of time with pure exponential growth. Okay, any other questions?
I do have one.
Yeah, great.
It's the first problem in 5.6.
Yeah, let's take a look. Wait, 5.5?
Or yeah, sorry.
Yeah, no problem. Got me worried for a second. So did I assign 5.6? I shouldn't. Okay. Yeah, so the first problem is it's working with this same formula. And you'll notice this is really similar. This is our continuously compounded interest. but it's also exponential growth or exponential decay. A lot of times we use different letters in the situation. So the A and the P and the R match up with sort of financial terms or variables. But it's exactly the same relationship here, where this is what we would think of as exponential growth, where B is like the growth constant, A is this initial value. So don't get mixed up by the changing variables. It's really the same steps, the same relationship. So in that problem, they're just, the first problem, they're just asking us to kind of rearrange this equation for our different quantities, right? So solving for P, I can just divide to get P alone. But if I'm solving for T, that's a variable here, I've got to start by dividing both sides by P. And now I can do the same kind of trick I did before, where I change this to an exponential, sorry, from an exponential to a logarithmic. So that's really kind of the way we've solved the last maybe 3 problems that we've seen, right? And that was kind of our first trick that we saw with exponential and logarithms, is being able to convert between them. So like I said in the beginning, this is really the technique number 1, right? To know from exponential and logarithms. It doesn't work for everything, but it works for a lot of things, and you're going to need to know that to be successful. So, right, and then you can solve this or rearrange that to get T.
Thank you.
You're welcome. Okay, here's another one I got. 5.4, number 12. Yeah, so it turns out this one, so number 12 says you invest $2,300 in an account at a rate R, which they tell you is 0.046, and it's compounded continuously. So that's back to our A equals P e to the RT. And in this case, they want to find the time it takes to triple. Well, to both double and triple, right? So this is very similar to the other problem, right? So we just have to plug in these values into here, and then right, set that up as this needs to be double. So we do one of them where that's 4,600 and one where it's tripled, 6,900. E, and then our rate times T. Okay. So that's, again, from there you'll solve those the same way.
What?
Yeah, and then that number 2, we did one that like that already as well from a similar one. So yeah, was there another question or a comment on this?
I have a question. Can you do 5.3 questions 13 and 14?
Yeah, take a look. Yeah, so very similar questions. I think if you see one of them, you'll know how to do the other one. I'll give you something similar. Let's say log base b of 7 equals 4.2. Log base b of 11 equals 5.1, and the log base b of 2 equals 1.3. What is the log base b? It's not the best example here, but this works. 44. And it's really the idea that they want you to be able to see is that we can rewrite logarithms by breaking down this. It's called the argument, the part that's inside the logarithm. And so remember, the log of a product, doesn't matter what the base is, the log of x times y is equal to log of x plus the log of y. So that's what we want to do here. We want to break it down so I'm able to use these facts. And 44 is 4 times 11, right? So 2 times 2 times 11. So I can break this up and just add those together. Log base b of 2 plus the log base b of 2 plus the log base b of 11. All right, so I'd add those values together. And that would give me this value. So, you know,
So I have a question.
yeah.
Yeah, what if it happens that it's in a situation where the numbers are not like cannot break down?
Well, then we couldn't use, it wouldn't be a problem like this. It'd be some other, you'd need to know either what its parts are, like this problem, or you'd need to do some other information. So you couldn't, if it doesn't break down, then we don't know. So if you don't know the base of the logarithm and you don't know the value, then that's too many unknowns. But here we're able to do that one because of the information they give us.
Okay, thank you.
Mm-hmm. Other questions?
I was wondering for the quiz, the number 14.
Number 14 on the quiz?
Mm-hmm.
Yeah, so what they give you there is they give you, and again, I don't want to go too far because it's our quiz question, but they give you this formula. This is the symbol they use for decibels. And they tell you that this initial, or I sub 0, is 10 to the minus 12. So those are facts given in the problem. And this is like the baseline. This is the intensity of the smallest, or the sort of faintest sound that we can hear. And so what they do is they give us different values of I and ask us to compute the number of decibels. So if I feed you an I value like 10 to the minus 3, I would plug that into this formula. I just need to make sure I use my rules of exponents there. All right, so I would bring that up and add that. So plus 12 would give me 9. And remember that the log here actually has a base 10. It's a common logarithm. So the log base 10 of 10 to the 9, that's going to give me just a 9. And that's the inverse property of logarithms. When the base of the logarithm and the base of the exponent are the same, right? The log and the exponent neutralize each other. So that would give me my number of decibels. Decibels range from 0, I don't know, up to 200 or something. 200 is like really, really loud, like ear damage loud, but something like that. Okay. And this is, you know, this is called a logarithmic scale. So there are certain physical properties like decibels that if you try to do them with a linear scale, they just wouldn't really work. The values are too spread out, or they change, the number of decibels changes too slowly. So it's true of decibels, it's also true of earthquakes. Earthquakes are always also on a scale like this. So they use logarithms. We talk about a 7.9 earthquake. That's has a different relationship to like a 7.8 earthquake. Other questions? It's a good start here. I just wanted to talk just a little bit about logarithmic equations. I summarized, you know, exponential equations are 3 kinds of approaches here. We have the same type of thing with logarithmic equations. So the first and easiest type to solve are this. If you have the same logarithm and they're equal to each other, then you can just set the insides or the arguments equal to one another. So that's certainly nice. If I have the log base b of x equal to some number k, right, this would be a conversion. I would want to convert this to an exponential. If you have, we don't see these as much, so it's probably not worth I think those are the only kind of 2 types that we would work for, but more common in logarithms, we have to use the properties of logarithms. To rewrite these. So, and remember what those do. A lot of times when we're using properties of logarithms in this situation, we would be working this direction, we would be combining them together into a single logarithm. Sometimes we work the other direction, splitting them apart, but with logarithmic equations, it's usually easier for us to have fewer logarithms. So we would want to take kind of two logarithms and combine them if possible. And you should be very comfortable with these rules at this point. And log base A r times log base A of x equals log base A of x to the r. So those are just our same properties of logarithms, but kind of written or shown in a different direction, right? That's, we typically are moving this way when we're working with these logarithmic equations. For example, the log base 2 of x plus the log base 2 of x minus 1 let me make that x squared x minus 2 equals 3. I think this will work out. I may have messed it up, but I think I've got the numbers right. So when I see this, I'm thinking, can I do either one of these? And it turns out this first one isn't really going to work for us because I have this constant sitting here, right? If this weren't here, I could have moved this over and used that relationship, but this constant here is not allowing me to do that. When I look at or think of my second approach, I need the logarithm equal a number. On here I have two logarithms, but I know, since we just wrote it down, right, I can take those two logarithms and combine them into a single logarithm. So this becomes the log base 2 of x times x minus 2. Now we're in a good spot, right? Now that looks just like this. You have to convert it. I see way too many students who sort of get to this point and then they just like drop the logarithm. I don't know, they pretend it never existed or something, but that's not what happens. We have to convert this to the exponential. So this becomes 2 cubed equals x squared minus 2x. Right, 2 cubed is 8. So when I subtract the 8 over, I get this.
So you FOILed that first before you wrote that next equation?
I did. I mean, you
Okay.
don't, you could do that in an extra step. I just was sort of saving a step there.
Okay.
But yeah, it didn't have anything to do with the conversion. Right? It's the 2 cubed equals this. And then I just rewrote that as like you said, I distributed it. And I did that partly too because I'm getting a quadratic here, and so I know I need to set that equal to 0, and hopefully it solves by factoring, which it does. X equals 4 and x equals minus 2. Now, there's one little detail at the end that probably, hopefully you've learned, but it may be the kind of hard way from, making some mistakes or not getting the right answers. I did all my work correct, but these answers aren't guaranteed to work in my original problem. So I need to check them and make sure that they don't make anything negative. So if I put in 4 here, that's fine. Log base 2 of 4. I know what it is. You don't need to know what it is. That's fine. And log base 2 of 4 minus 2, which is 2. So that's good. I don't have to check the whole thing. I just need to make sure that nothing is made 0. Now when I put in minus 2, all of a sudden that's bad. I can't take the log base 2 of negative 2. So that one ends up not being a solution. If either of these values make anything here negative, it can't be a solution. Questions on this one? Another kind of relationship I want to make sure that you're aware of if we say like f of x equals 3 to the x, as long as the base is positive or bigger than 1, we get a curve that looks like this. If the base is less than 1, then it looks a little different, right? It's actually decay in that case. But in this, for this example, let's just assume that. You want to remember that the logarithmic, the sort of corresponding logarithmic function would be the log base 3 of x. And that is the inverse function of f. So the inverse functions, remember I switch the x's and the y's. So notice with this exponential function, the domain here is all real numbers. Right? I can put any x I want to into here and I'll get a value out, positive or negative. But the range is only from 0 to infinity, and it doesn't include 0. So an exponential function like this, 3 to the x, k to the x, never equals 0. While the logarithmic function, you can switch these around because that's the way inverses work when you have domains and range. So the domain of a logarithmic function is the range of the exponential. So the domain there is only from 0 to infinity. The range is equal to the domain, which is all real numbers. And it's good to have this kind of image or thought in your head of the logarithm. So you cannot put a negative value into a logarithm because you cannot get a negative value out of an exponential, and they are inverse functions of each other. Sometimes you will see questions that say, what is the domain of, say, the log base 2 of 3 minus 2x? So it'd be theoretically possible to think of this as like a transformation of this basic logarithm function and try and figure out what the domain is. But this one's actually kind of hard with the 3 minus 2x. It's much better to just say, well, what's inside there, whatever it is, has to be bigger than 0. So the domain of this logarithm is where the expression inside is always bigger than 0. So that's 3 bigger than 2x divided by 2 is x less than 3/2. So it'd be from minus infinity up to 3/2. So those are just like a couple points I don't think we had touched on with logarithms that I wanted to make sure to mention. This idea of a domain, of how to solve those logarithmic equations, and then also this connection between logarithms and exponents. That's really where logarithms come from, and the usefulness of logarithms and exponents are because they go together. They're like they're inverses of each other, right? It's a pairing. Okay. Any other last questions?